Welcome back, everybody. So just so you guys know, the interim grades get pulled on Wednesday for LOP and everything, but that doesn't affect anybody in here. The only thing that I will have to say is when we get to grade pulls, like at the end of the 9 weeks, those of you taking this for CCP, you should ignore what you're getting in Canvas. I have to go and change that for Stark State. So I will have to do the Stark State grading scale, which will make your grade a little bit different. It should be very close to what you have already. But in terms of like the A minus, there is no minuses, there's no B pluses. It's just A, B, C, D. So I'll have to change it a little bit, but you'll see it. I'll tell you ahead.
Is it just 90 to above?
90 and above is an A. Yeah, 90 to 100 is an A. 80 to 90 is a B. Yeah. That's why, it's kind of nice if you get like the 92. It's like, oh, okay, that normally would be an A minus. But if you get the 89, it's like, oh, shoot, 1% away would be an A, but you get the B, flat B, not a B plus. Okay, so we're into chapter 2 now. Chapter 2 is when we really start to get going on like what calculus really is, like the really, meat and potatoes. Yeah, I use that term a lot. It's like the meat and potatoes of what calculus really is. We talk about chapter 2. In chapter 2, and we spend a long time in chapter 2. I think there's something like 10 sections in chapter 2. And we'll do several quizzes along the way. Remember that we only get through 3 chapters in a semester. So by Christmas time, we will just be getting to the very finish of the very ending of chapter 3. So we'll be in chapters 2 and 3 for a long time. I think we do like a midway through chapter 2 test and then a rest of chapter 2 test. I believe so. I don't quote me on that, but I believe that's what we do. We do several quizzes in there as well. The overarching idea of chapter 2 is learning about limits and derivatives. Okay, limits and derivatives. The hard part about chapter 2 at the beginning in sections 2.1 and 2.2 is that I have to teach you like the hard way to do these problems. And then in section 2.3, I'm like, hey, let me show you the easy way to do that. So in section 2.1, it's all about like the idea of how to do these problems. Section 2.2, we go through like the nitty gritty of it and try to, actually solve these problems using the long methods. And then chapter 2.3, I kind of give you like a shortcut to do these things. And then you guys kind of hate me a little bit for working so hard in section 2.2. All right, so let's get to it. There's 2 types of problems that we're going to talk about today. The tangent problem and then the velocity problem. And they relate to one another, and hopefully you'll see that by the end of the day today. The first one, let's talk about what a tangent is. What a tangent is. When I say the word tangent, you probably think of like opposite over adjacent tangent, like trigonometry tangent. But that word tangent doesn't just have its implications in trigonometry. You also might have heard it in geometry as well. The tangent, or a tangent, is a line that lies directly next to a circle. Okay, it does not intrude into the center of the circle. It does not go into the circle. It just lies directly next to the circle. So I've got a diagram down here, right? That line T is just butting up to the circle. It doesn't intersect it. It doesn't go into it. It's not a secant. That's what we would call it. It's not a secant. It's just a tangent. It just lies directly next to it. Okay, you could say that it intersects it once. It doesn't go through it, but it just crosses once. It just lies directly next to it. Because when I say the term intersect, that means that it shares that point. It shares that one unique point where it lies directly next to it. Okay. Now, when I say intersects it only once, I have to be careful with that when we expand it to more algebraic things, because if I change my definition going from like the more geometric definition of a circle to more like a function, and I say, okay, what's a tangent to a function? Now, does that cross it just once? No, it actually crosses it twice, right? And also, doesn't this line L also just cross it once? So we just have to be a little bit more careful and use our intuitive definition of a tangent and say, okay, it's going to lie directly next to the curve. Okay, it's going to lie directly next to the curve. Okay, I always like word origins. The word tangent is derived from the Latin word tangens, which means touching. Just means lying directly next to. It's just touching that curve or that circle. Thus, a tangent to a curve is a line that touches the curve. In other words, a tangent line should have the same direction as the curve at the point of contact. And that's a really unique, to me, that's really cool. It has the same, almost like vector to it. It has the same direction to it. Like I think about it this way. Like if you had a sling and you had a little, like a ball in a sling, right, or a stone or whatever, and you threw that stone, and you were circling that sling, right, and that stone came out of it. The instant where that stone comes out is the tangent line of that circle to where it was going. Basically, like the force, it would go out tangentially from the circle that you were swinging. Okay, or you could think about it this way: if something is orbiting around the Earth, right? If there's a satellite there, or maybe like a rocket out there orbiting around the Earth, and you wanted to break orbit, right? You wanted to break orbit. You would need to burn the rockets at some point so that if you wanted the direction, maybe you were going out to the moon or something, you wanted the direction to go out to the moon, you needed to figure out, okay, where do I need to burn the rockets so that I would go out tangentially to go to the moon? Okay? You would need to go and say, like, okay, at that point. And at that point, it would have that same direction. Okay? So that line at that curve is having the same direction to it. If I change that point along the circle, that line would start changing around the circle as well because it would have the same direction to it. If I manipulated this point along the curve, that line would start, having different slope to it. And that's going to be very important. We're going to talk about slope a lot as it applies to tangents as well. And we talked about going circle and changing it to algebraic. Okay, I think we can get to this problem right here. So this is really the tangent problem and how it relates to something algebraic. Find an equation of the tangent line to the parabola of y is equal to x squared at the point 1, 1. You're going to see this a lot. We're going to have this type of problem, through the end of the year. Calculating the equation of a tangent line is extremely important. It's one of the most fundamental questions that we answer in calculus. Finding the equation of the tangent line. You have no idea the implications right now, but that is a huge question that we ask all the time in calculus. So let's take one of our most basic functions, the parent function y is equal to x squared, and we're going to say, okay, well, if we had, let's spread this out here, 1, 1. So this was at 0, 0, 1, 1, maybe 2, 1, 2, 3, 4, somewhere up there. And we just mimic it on the other side, right? Okay, we are saying that at point 1, 1, and I always have to give you a location where I'm saying find the tangent to that curve at. Okay, so at point 1, 1, find the equation of the tangent line. Let's sketch it in. Let's see. Okay, I'm going to use my line tool here. I'm going to have to manipulate the other side of it too. Okay, maybe come up this way a little bit, go down, go up. There we go. That looks pretty good. And this is just a rough sketch of it. Right? Would we all agree that that is touching the curve at 1, 1? And I wouldn't want to make that slope any steeper because it would probably intersect twice. And I wouldn't want to make that slope any shallower because it would probably intersect twice on the other side. Okay, so what I would like to do, if I want to find the equation of that tangent line, to find the equation of a line, one of the most key pieces that we need is the slope, correct? We need to find the slope of that line. Well, remember that slope is change in y over change in x, right? Delta y over delta, change in y over change in x. y2 minus y1 over x2 minus x1. Well, and I know I have the coordinate 1, 1. But do I have another coordinate on that line? No, I don't. I don't know any other coordinates on that line other than I know that it runs through point 1, 1. I could guess and say, like, okay, maybe the y-intercept is down there, but I don't know for sure. So how do I calculate that slope then? Well, if I know 1, 1, I can use the rule of the function, right? Because if I think about x squared, y is equal to x squared. If I plug in x, what's my output? X squared, right? I know I have this coordinate, x comma x squared. Input x, output x squared. So what I can truly say is that if I want 1, 1, then I'm going to say, okay, y2 minus y1, x squared minus 1 divided by x minus x1, x minus 1. And I'm getting this 1, 1 from the coordinate that I chose to find the tangent at. That is going to get me my slope at the x value that I choose. Now, how am I going to choose those x values? Well, I am going to choose those x values that are going to get closer and closer and closer to 1. Like, for example here, what if I picked an x value of 2? What if I said, okay, let's find at 2 comma. Well, if my input is 2, along my parabola, if my input is 2, what's my output? 4, right? So basically what I'm doing here is finding this line. That's the slope that I'm finding. Okay? So let's run those numbers then. That would be 4. Ooh, what is that? Get out of there. This would be 4 minus 1 over 2 minus 1. X squared is 4 minus 1, 2 minus 1, because it'd be y2 minus y1 over x2 minus x1. So in this case, 3. My slope is 3. But is that the correct slope that I want for this line? No, I need it to be just a little bit more shallow, right? So what are we going to do? Well, let's try to decrease that value. I picked 2, and that was way far out there. Maybe 1.5 would be better. And I'm going to cheat here, and I'm going to say 1.5 comma 1.5 squared. Because that's the xy pair that I would have. So that would be like saying, okay, I've got 1.5 squared minus 1 over 1.5 minus 1. Let's see what that turns out to be. Let me get out my calculator real quick. Come on. There we go. So we have 1.5 squared minus 1 divided by 1.5 minus 1, or 0.5. 2.5. So my slope here is 2.5. But is that the exact slope that I want? Not necessarily, because I've still got some error in there, right? I picked this point, comma, this point, somewhere in there, right? I want to get it onto that line. This is still too steep of a slope. I need it to be shallower. So maybe we should pick, I don't know, 1.1. Okay, well, that would be 1.1 squared minus 1 over 1.1 minus 1. Okay. 1.1 squared minus 1 divided by 1.1 minus 1 is 0.1. 2.1. The slope would be 2.1. So what I can really do is decrease and decrease and decrease and decrease that number. I could keep getting my x value closer and closer and closer and closer to 1 to make that slope look even more and more and more look like that line, right? That's the idea of a limit. I'm going to keep getting closer and closer and closer and closer to something until I can say that I am sufficiently close enough to assume that that's where it's going to go to. That's the idea of a limit. It's almost like the idea of an asymptote, right? We talked about that. We can get closer and closer and closer to something as I keep going on. So take a look here. I copied these tables out of the book because I'm a little bit of a cheater there. We ran the 2, we ran the 1.5, we ran the 1.1, but look, I can keep making that value closer and closer and closer to 1. Why am I getting closer and closer to 1? Because that's the location that I was looking for. That's the true slope that I want. And what do we think it's going to even out to? 2. Do you see how it keeps getting closer and closer and closer to 2? So we can say the limit as x approaches 1 would be 2. Okay, now, I chose 2 on the far right side. What if I had chosen 0 and worked my way forward? What if I said, okay, chose 0, and then 0.5, and then 0.9, and then 0.99, and then 0.9999, and kept that going and going and going? What does it look like my limit is going to? 2. And that's the idea of a limit. That's the idea of a limit. Getting closer and closer and closer to something, not only on the right side, but also on the left side, until they converge to be one thing. So we can see here, after running all the numbers, that's the hard part about right now. Right now, we actually have to physically go through and run all the numbers. Soon enough, I'll give you a shortcut on how to compute that without needing to do this. But for right now, we're saying, okay, as we get closer, closer, closer to 1, both from the left side and the right side, I approach 2. So I can assume that we are going to get to 2 with our slope. Now, the slope is 2. We say, okay, we decide that the limit is going to reach 2. Okay, it's 2, and we've got the coordinate 1, 1. Right? We've got the slope and the point. From this point on, we can make our equation of our tangent line pretty easily. Now, you're going to find I, more often than not, use the point slope method to make my line. I use the point slope method to make my line. What do I mean by that? Y minus y1 is equal to mx minus x1. Because we're going to have to do this process a lot. Finding the slope, creating the tangent line. Finding the slope, creating the tangent line. This is the best route to take, I promise you. That's the easiest way to do it. So I'm going to plug in. I'm going to say y minus 1 is equal to 2x minus 1. x1, y1, slope of 2. Distribute to 2. Add the 1. So the equation of the tangent line at 1, 1 of x squared is y is equal to 2x minus 1. Again, how did we do that? We said, okay, we found the point 1, 1, and then we just started running slopes. We found slopes that were very, very close to 1, 1. And we did it just by narrowing our focus from something bigger than it down to it, getting closer and closer to it, and also going from the short end, going from the smaller side, going from 0 up to it. So going from the left side and the right side, it's converging to 2. And then at that point, once I decide that the slope is 2, once I can see the pattern and say, okay, it's 2, we can actually make our equation of our tangent line. Now, how did we do? Did we do pretty good? 2x minus 1? I'd say so. I mean, it's a little off, but say there's negative 1, slope of 2. Yeah, that looks pretty good. So it looks like our sketch was pretty accurate. Now, this is the same exact problem. I'm not changing the graph or the line at all. But what I'm showing you here is that as I get closer and closer, I can make those values arbitrary. And I can say, okay, if I'm at Q over here, say this P I chose was 1, 1 again, but I'm at Q, I can take Q closer, 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 closer to P. I want Q to approach P. I want it to get closer and closer and closer to that value that I'm trying to find the tangent at. And that will give me as close as it possibly can be. And it's close enough for our purposes until we see a pattern. And I do that from the small end too. Look, the Q over here is negative. And I just keep dragging Q along the line until we get closer and closer and closer to P, until we see it converge to be the same thing. That's the idea of a limit. That's the idea of getting closer and closer and closer to something until it's there. It's at that point. This is another example. I don't love this example, but I wanted to show you one that was a little bit more real life here. The flash unit on a camera operates by storing charge in a capacitor and then suddenly, instantaneously releasing it to set off the flash. Okay, that bulb, it stores up that energy, stores up electricity, And then, boom, at that moment that we want to snap the picture, it sends it to the bulb and that makes it go off really bright. The data in the table describe the change Q remaining in the capacitor at time t. Really, this doesn't really need to make sense to us. All we really need to know is that what we have here is a sudden instantaneous release of energy, and the bulb goes off. Okay, and that's going to be very important, this whole idea of things happening instantaneously. Okay, use the data to draw the graph of this function and estimate the slope of the tangent line at 0.04. Okay, I'm going to be a little cheater pumpkin eater here. There's my graph. Da-da-da-da. Done. There's my graph of that table. Okay. What we're saying here is that at 0.04, what is the instantaneous change? What is the instantaneous change of release of electricity to the flash bulb? Okay? The instantaneous change is going to be the slope of the tangent. Whoa, I need a pen. The slope of the tangent line at that moment. Okay? When those 2 points meet there, and I tried to draw it a little bit further away because the line is kind of a shallow curve. Okay? Use the data to draw the graph. Done. Drew it. There we go. And estimate the slope of the tangent line where t is equal to 0.04. Now, when it asks you to estimate the slope of a tangent line, what I need you to do is figure out, okay, I don't have the actual equation where I did last question, right? I don't have y is equal to x squared that I could plug in the numbers. But what I do have is a table of value of coordinates. So what I would like to do is say, okay, find the slopes around there. And we're going to find average change around that point. We're going to say, okay, at 0.02, comma 81.07, we're going to find the slope between these 2 points. And then we're going to do the exact same thing between these 2 points, because it's got to be somewhere in the middle there, right? It's got to be somewhere in the middle. It's got to be a little bit above our low estimate, and it's got to be a little bit below our high estimate. And that's what it does in this table. Again, I copied this table from the book here. Oh, there we go. And we say, okay, look at what we have here. This is the value that we're using, the coordinate that we're using. So here are those coordinates that I circled above, right? The 0.02, 81.87, and the 0.06, 54.88. We're saying, okay, between these 2 points, right there, and 0.04, 67.3, these are the corresponding slopes. So what we're calculating in this table is the slope between here and here, and then calculating the slope between here and there. Because the slope on our instantaneous change at 0.04 is going to be somewhere in the middle there. So the book says, well, if it's somewhere in the middle, let's take the average. Let's take 1/2 the sum of negative 742 plus negative 607.5. That's what the book does. They're like, well, if it's somewhere in the middle, we'll just take the average, which is okay, which is not a horrible thing to do. We know that it's somewhere in the middle there, so we're just going to assume that it's somewhere in the middle, and I did this ahead of time, so it's negative 674.75. Okay? It's somewhere in the middle there. And we're actually going to do that process a lot where we say, well, if it's somewhere in the middle, it's got to exist somewhere in the middle so we can use the average. But understand that this is actually just doing this process is just actually finding the average of it. Is this truly instantaneous? No. This isn't truly instantaneous because what I had to do is I had to find the slope between the point above it and the point below it and average them out. So how do we find instantaneous then? Well, that's what we spend the rest of chapter 2 on. How do we find instantaneous? Instantaneous, we need to decrease and decrease and decrease and get closer until it's negligible. And do it from the other side. Get closer and closer and closer until it's negligible. So what we have to do throughout the rest of this chapter is, first of all, find the mathematics behind finding a limit of something. And how do we operate with that? And then how does that tie into finding the tangent line? Okay? That's like the rest of chapter 2. So we said this is going to be the tangent problem and the velocity problem. So let's switch gears a little bit and talk about velocity. Well, remember that velocity is just the change in speed as it relates to time, right? It's the change in speed as it relates to time. If I change my speed, change in position as it relates to time. I said that wrong. Change in position as it relates to time. If I change my position as it relates to time, that must mean there's got to be some velocity. Right? Change in speed as it relates to time would be change in acceleration, right? If I change my velocity, therefore I'm changing my acceleration. How many of us are in physics right now? Some of you guys? You use a ton of calculus in physics. Because you're going to find soon enough that derivatives and integrals of these position and acceleration and velocity, they're all tied together. So take, for example, if you watch the speedometer of a car, okay, you're driving on 77 and you're watching your speedometer, you're watching your speed, maybe it goes a little bit too fast. You're watching the speedometer of a car as you travel in a city traffic or you're on the highway. You see that the speed doesn't stay the same for very long. As soon as you let off the accelerator, the speed goes down. As soon as you get back on the accelerator, the speed goes up, right? It doesn't stay the same for very long. It's constantly changing. That is, the velocity of the car is almost never constant, even if you keep your cruise control on, right? Even if you keep your cruise control on, it's going to, as soon as it dips below a certain speed, it pushes back on the accelerator so you go back up and correct it, right? As soon as you go above a certain speed, it pushes you back down a little bit, right? That's what cruise control does. So it just keeps you within an acceptable boundary. So your speedometer is never giving you truly instantaneous velocity. Your speedometer is never truly giving you instantaneous velocity. But what it is giving you is average velocity. It's giving you average velocity from time to time. Okay? We're going to have a problem a little bit later on in the year. We're going to say, like, okay, if you travel down to Columbus and using 120 miles and you get there in 2 hours, your average speed is 60 miles per hour, right? Could you go above that at any point in time? Yes. But if you had gone above 60 miles per hour, shouldn't there be a point where you had gone less than 60 miles per hour to make that even out? That's that idea of having average velocity. And what we're going to be doing is saying, okay, instead of taking the observation over the course of 2 hours, let's go over the course of 1 hour. Let's go over the course of 30 minutes. Let's go over the course of 50, and we keep making that closer and closer and closer and closer until we get to something called instantaneous velocity. So let's take, for example, here. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Ooh, I shouldn't show that real quick. Just keep that right there. Find the velocity of the ball after 5 seconds. Now, this is an equation. This S of t is equal to 4.9 t squared. That's, for those of you in physics, that should probably be a familiar equation to you. That's the acceleration due to gravity in meters per second of a falling object without any initial velocity, without being thrown or anything. That's just dropped, right? Without any force applied to it, just the force of gravity acting on it. So find the velocity of the ball after 5 seconds. So here's what we're going to do. I'm going to find the velocity of the ball at time 5 seconds and then at time 6 seconds, and then find the average of it. Okay? Because wouldn't we agree that velocity is change in distance divided by change in time, right? Velocity is change in distance divided by change in time, which should like ring a bell back to slope, right? Change in y over change in x. Change in distance, oh, I still can't scroll down. Change in distance divided by change in time. All right, well, if I want to change distance and change in time, well, excuse me, I would need to take the time from 5 seconds to 6 seconds and find the average velocity in there, right? So at time 5 seconds, where is it at? Well, at time 5 seconds, it's 4.9 times 5 squared, right? And the x value that corresponds to it, and actually let's go 6 to 5 seconds. Oh no. Yeah, never mind. That's right. 4.9 times 5 squared over 5, change in time, minus 4.9 times 6 squared. I think I should change those around because if I don't, I'm going to get a negative. Right? I want to go time A to B, or B to A, excuse me. I'm going to do this instead. I'm going to go here to here. Oh, it still would have worked out because I would have gotten a negative on top and on bottom and it would have canceled out. Oh well. It would have worked out either way. So what I'm running here is saying, okay, this is plugging it into this equation at 5 seconds and then at 6 seconds. 4.9 times 6 squared minus 4.9 times 5 squared. And I'm dividing that by the difference of 6 and 5. 1. 53.9. The average velocity from time 5 seconds to 6 seconds is 53.9. Is that instantaneous velocity? No. That's average velocity at time 5 seconds to 6 seconds. That's a whole second apart. That's a long time in terms of being dropped, right? Speed can change a lot in a second as it's being dropped. So what if I decrease that value? What if I say, okay, no, let's not take it from 5 seconds to 6 seconds. Let's take it from 5 seconds to 5.1 seconds. Let's make that time interval a little bit smaller. Well, then I would just be replacing that 6 and the 5. Well, the 5 would stay the same. 4 times 4.9 times 5.1 squared. And then this would be a 0.1, right? So this would be the same thing in here. But instead of 6, this would be 5.1. 5, insert 0.1. Now I'm dividing it by the difference between 5.1 and 5. 49.49. Next.
This might seem like kind of a dumb question, but why don't you just do 4.9 like 5 to the second and then just divide that by 5? Like, why do you have to find the average between them?
Because dividing that by 5 would give you the average velocity over the whole course of 5 seconds.
And you're just trying to find it where.
And I'm trying to say
seconds?
at 5 seconds, at what is its speed at time 5 seconds? That's the question that I'm asking.
Okay. So if you
Does that make sense?
Okay, so if you weren't finding the difference between it, it would just give you the average velocity over the first 5 seconds then?
Right, over from 0 to 5.
Okay.
You know what I mean?
Yeah.
And what we want is, okay, at time 1, 2, 3, 4, that instantaneous moment, what's its speed?
Okay.
Does that make sense?
Yeah, that makes sense.
So that's what we're looking at. I know, I got it. Yeah. So that's what we're really trying to find here in this calculation. What is the instantaneous velocity at time 5 seconds? Well, do you see how I could keep this process going? I could say from 5 to 5.1 seconds. What if I made that interval smaller? From 5 to 5.05 seconds. What if I made that interval smaller? What if I made that interval smaller and smaller and smaller until it's negligible? Until we see a pattern. Until we see a limit existing. What is the limit as I keep getting closer and closer to 5? What do you guys think? 49. And that's what we have to do with our calculations for right now. For right now, we don't know any other way other than just keep running the numbers and running the numbers and running the numbers until you see a pattern. Until you see a pattern arise that you can say, well, I'm going to say that the limit as I get closer and closer to 5 is 49 meters per second. And that's what we have to say. Now, how do we find that more precisely? How do we actually calculate that more precisely? That's the rest of chapter 2. That's like the rest of chapter 2. But for right now, all we can do is just keep running the numbers. We got to keep plugging and chugging and say, okay, we're going to keep finding slope and finding slope and finding slope and finding slope until we see a pattern arise. Okay, that's the idea of a limit. Now, I wanted to say something about something that you calculated, we've calculated before. This whole difference quotient thing. Remember doing that in chapter 1? We may have the feeling that these calculations used in solving these problems are very similar to those used earlier in this section and even in the past chapter. There is a very close connection between tangent problems and the problems finding velocities. You're going to find that instantaneous change in position will give you velocity. Instantaneous change in position will give you velocity. And also, for those of you in physics, instantaneous change in velocity will give you acceleration. Instantaneous change in position will give you velocity. Instantaneous change in velocity will give you acceleration. So if you can calculate that, if you know how to calculate that, that's very, very, very useful. Okay? Now, thinking back to what we did in chapter 1, that whole difference quotient thing. This is that f of a plus h minus f of a over a plus h. Look, over h actually. Look, those a's cancel out. Running that slope formula will actually give you a difference quotient. Running that slope formula will give you a difference quotient. Well, what is a plus h then? A plus h is your difference interval. A plus h is the difference in the amount of time that you take. Like, for example, we were going from like 5 to 6 seconds. That a plus h would be 1. We were going from like 5 to 5.1 seconds. That difference in there would be 0.1. 5 to 5.001. That difference would be 0.001. You're actually calculating difference and difference and difference and difference and difference and difference until you get closer and closer to the difference that would be negligible. A difference that would be so close to the real thing that you can just assume that it's true. Okay? That's the idea of a limit getting closer and closer to something that you can say that it's just going to be that thing. Okay? All right. That's all we have for the lesson for today. Let me turn off the video here.